Before starting, I would like to thank the organizers for calling me and for organizing this, because it's so good to be in front of people, to see your faces, just not the eyes, but also the mouth as well. So, okay. So I will speak mostly about what we have been doing in this last, mostly just COVID years, closed in the labs, so far away from direct collaboration with conservators by the end of it. So you will see that we moved more and more toward more simplified model systems. This is because this is what we tend to do if we are not controlled. So the first time that our group with my collaborators at University of Pisa started thinking about the molecular transformations of oil paintings and the consequence that this may have on the conservation of a painting was during the CMO project. In the project, we were investigating into the cleaning of modern oil paintings, and at the time, one of the main conservation issues that we were researching into was water sensitivity. So paint layers, oil paint layers, were sensitive to water and other polar solvents. So if a cotton swab that was imbibed with water would get in contact with the paint layer more or less, for a more or less prolonged time, then the pigment particles might get picked up. When we started the project, we knew that there were some reasons that were related to calcium carbonate, which is an additive of certain brands. And this, by the action of SO2, might transform into epsomite, which is very soluble in water. And so when you apply the cotton swab with water, then the epsomite becomes dissolved, and then the cohesion of the paint layer is disrupted. But then we also knew that, my colleagues knew, I didn't at the time, that there were paint layers that were sensitive to water, even if they did not contain any magnesium carbonate in the first place. So by the end of the project, we became quite convinced that this was related to the molecular structure of the cross-link fractions. And in particular, if the cross-link, the polymeric network of a paint layer was not very polar and well cross-linked, then the paint layer was quite stable. But if the cross-link fraction was not very extensively cross-linked and was polar, then in that case it was sensitive to the action of polar solvents, might swell up when the water was applied, the water would solubilize what is soluble, like diacids, for example, and then the pigment particles might be getting picked up mechanically. We learned that there were pigments that were never associated with water sensitivity. One of them is lead white. We also saw that there were pigments that were often associated with water sensitivity, not always, but often, and among them we have ultramarine blue. And we also learned that exposure to high levels of relative humidity actually does not just favor hydrolysis, but also oxidation of a paint layer. So by the end of the project, we came across the perfect set of samples, let's call it. It was ultramarine blue from Winsor & Newton. We prepared just straight from the tube model paint layers, and they were just left to cure. So one set was kept in normal condition, and the other one was exposed to high relative humidity conditions. So the control that was not artificially aged was not water sensitive, and the one that was exposed to high levels of relative humidity became water sensitive. Okay, so we have two paint layers which have got exactly the same age, come exactly from the same paint tube. One is not water sensitive and the other is water sensitive. And so we started our analysis with our, let's say, standard instrumentation in our group. And at the beginning, it was surprising to see how similar everything looked between the two. First of all, there is no real difference in the water content. Despite one paint layer was exposed to a high amount of water, that did not contain more water than the other. There was no significant amount of magnesium sulfate in the paint layers. And also, the paint layer that was exposed to high levels of relative humidity was not significantly more hydrolyzed than the other one. Actually, the soluble fraction of the non-water sensitive layer was more hydrolyzed than the other one. The first more interesting difference is that the artificially aged sample contains more reactor double bond. So the curing, let's say, was a little bit behind the other one. And then a very strange behavior during pyrolysis. When we do pyrolysis, we use a silylating agent, and the water-sensitive sample was not derivatized. The polar moieties of the water-sensitive sample were not derivatizing efficiently. And this was a consistent behavior. We kept repeating the analysis, and while the non-water-sensitive one was perfectly behaving, all acidic moieties were derivatized, this was not happening with the water-sensitive one. So maybe, because there is no more water in the paint layer, maybe there are other polar moieties in the paint film that we can't pick with our techniques that are hindering the reaction yield. So we went to talk with our NMR colleagues, and it's the group in our university of Marco Geppi, and I asked him, can you please give me the elemental analysis of this paint layer? Tell me how many carbons, how many oxygens are there, how many hydrogens, and also give me the speciation, carbonize, and everything else. And he was laughing at me because apparently you can't do this with NMR spectroscopy on such complex samples. Anyway, the thing is that they came with very interesting results, I think, because here we could see several differences between the paint layers. They said, okay, we can pick two main fractions. One is more mobile, and the other one is more rigid. The mobile fraction is constituted by monomers and oligomers, while the rigid fraction is constituted by the highly cross-linked network. And first of all, we have a difference in the amount of mobile fraction and rigid fraction in the non-water sensitive and in the water sensitive paint layer, because the water sensitive paint layer has got a bigger fraction that is more mobile, and also in the mobile fraction we have a higher amount of monomers rather than oligomers. This tells us that there is less cross-linking going on in the water-sensitive paint layer. Moreover, the mobile fraction of the water-sensitive paint layer contains also more unreacted double bonds, so clearly curing is behind. And also, in the rigid fraction, we have a higher amount of acidic moieties. And those moieties are acidic or in the form of metals, but they do not come from the hydrolysis of the polymeric net, of the triglycerides, but they are new acidic moieties. So the cross-link fraction of the water-sensitive sample is more oxidized than the non-water sensitive sample. So, okay, we have the degree of oxidation, let's call it for now, and degree of cross-linking of the paint layer that, and especially of the cross-link fractions of the paint layer that play a role in the stability of the paint layer itself. And so the question comes, can we understand what is the balance between oxidation and cross-linking in a paint layer? And can we tell when a paint layer is more oxidized and is more cross-linked? Because I think this is not just related to water sensitivity, but to lots of other conservation issues. We have seen several today, also weeping, dripping paints or liquefying paints, or also oxidation of the medium. This can, I believe that in several cases, this is related to a different degree of oxidation and cross-linking of the paint layers. So when we consider an oil paint, the molecular transformations, as Gwen was showing before, start immediately, because we have the curing reactions, so the reaction of the unsaturated chains with oxygen. And so the set of reaction is called oxidative radical chain reactions. They start with the addition of oxygen, and then they can evolve towards the formation of a polymeric fraction. But there are also other competing reactions that lead to the formation of oxidation products. And when I speak about oxidative degradation, is that because when oxidation takes place, we have the chain gets broken down, and so a small molecular weight fragment is also formed, which is volatile and may escape the paint film. So for me, it's more important oxidative degradation rather than oxidation, because the curing involves oxidation in the first stage. And actually, the situation is even more complicated than that, and there are several other reactions that we must take into consideration, which depend on the environment, on the pigment, on the drying conditions, and everything else. The point is that when an active species is formed, this may evolve towards cross-linking, may go in the direction of oxidative degradation, cannot do both. So the phenomena are competing. And so it is the balance between the oxidation, the reactions that lead to oxidative degradation and the reactions that lead to cross-linking that are fundamental to understand what is the state of conservation of a paint layer. And so understanding what is the balance between these two, it's really very difficult, because the molecular characterization of this paint layer, so the cross-link fraction of a paint layer, is really very difficult. And so we said, okay, maybe we can try to understand what happens in the longer time if we study the beginning, the curing, at the very beginning. This is part of the research that was carried out by Silvia Pizzimenti. She just defended her PhD thesis a few days ago. And the aim was to improve our understanding of the molecular features of a paint layer by studying its curing, and also to develop a methodological approach that can be used, let's say, to try to understand different aspects of these curing reactions. We worked with a combination of thermoanalytical techniques and mass spectrometric techniques. They involve treating the sample with different temperature, let's say, exposing it to different temperatures. And we work with fresh paints, very simplified model system, so oils and pigments, but then we also apply them on a glass slide and to prepare model painting layers. And they were analyzed for a long time. The fresh paints were subject to artificial aging with thermogravimetry, and the model paints were analyzed for a long time, very frequently at the beginning, and then more at bigger time intervals with time, up to maximum a couple of years. So one of the techniques that we like the most to try to understand the balance between oxidative degradation and cross-linking is isothermal thermogravimetric analysis under airflow. Basically, we take the fresh paint, we expose to a certain temperature. We work at 80, but we also did experiments at different temperatures, also ambient temperature. Just the analysis takes much longer time, of course. And we monitor the mass change of our paint. And so this is the typical shape of the oxygen uptake curve of an oil, of a drying oil. And what you see is that there is a mass increase followed by a mass decrease. And this is because of the reactions that take place. The mass increase is due to the addition of oxygen, which leads to an increase in the mass of the system. And then because oxidative degradation reactions lead to the formation of low molecular weight components, they escape the paint film, and so we have a mass decrease. The problem is that it is not straightforward to compare the curves obtained with different systems, because, for example, this is linseed oil and this is safflower oil, and then linseed oil seems to be taking more oxygen and this seems to be doing more oxidative degradation. So which system is more oxidized than the other? It's not easy to say. And so what we tried to do was to develop a model fitting equation that we could use to fit our experimental data, to give us quantitative parameters to compare different systems. With this equation, we can get kinetic parameters, but also we can estimate the amount of oxygen which is taken by the sample and the amount of mass that is lost because of oxidative degradation. We prepared our model systems. We studied safflower oil and linseed oil. It's been discussed already today. So safflower oil is rich in doubly unsaturated fatty acids, while linseed oil is rich with triply unsaturated fatty acids. And we chose two pigments, ultramarine blue, because it seems to be pushing oxidation, and lead white. The choice for lead white was driven by the fact that we couldn't think of any pigment that is absolutely inert. We couldn't think of anything, and so we said, okay, let's find something that we know something about it. And so lead white was an interesting candidate because it leads to stable paint layer, at least in terms of water sensitivity. Then metal soap is another problem, but we also know that it's a catalyzer. And so we compared these systems. These are our curves. This is the fitting equation that we used. On the left, we have linseed oil. On the right, we have safflower oil. And blue is ultramarine blue, and black is lead white. So the first parameters that we can obtain with this equation is the induction time. How long does it take for the reaction to start? And then we can also look at the apparent time constant of the mass increase step. So how quickly the reaction with oxygen goes on once it is set up. And so we can see that lead white catalyzes the oxygen uptake. This is known already from the literature, is a catalyzer. But we can also see that ultramarine blue reacts more slowly than lead white paint. But there is no significant difference in the speed of reaction when the oxygen uptake is taken up, is established between the two different oils. And then we look at the amount of oxygen that reacts with our system, so that is taken up by our system, and the amount of mass that is lost. And if we compare our systems, you can see that ultramarine blue paints uptake more oxygen than those based on lead white. There is a higher mass increase. And also that ultramarine blue is subject to more oxidative degradation. And this is especially true when safflower oil is concerned. So we have a higher mass loss, more oxidative degradation with safflower oil. So why does safflower oil have more oxidative degradation? We can find the explanation from this in the literature, because in safflower oil, there are the doubly unsaturated fatty acids, and they contain only one bisallylic position, while linseed oil contains triple unsaturated fatty acid with two bisallylic positions. And then we have a different reactivity between alkoxy radicals and peroxy radicals. And peroxy radicals may only abstract hydrogens in bisallylic positions, while alkoxy radicals, they may abstract hydrogens also in the other positions, which means that this is more reactive than the other. And when double bonds, when the bisallylic positions are finished, then the radicals need to find different ways of reaction. And if we look at those possibilities, we will see that peroxide radicals undergo other pathways of reaction which involve more oxygen and so more oxidation. So in general, if we have a higher concentration of the bisallylic positions, we have more cross-linking because hydrogen abstraction is favored, while if we have a lower content of bisallylic position, then we have a higher degree of oxidative degradation because the addition of peroxide radicals to double bonds is favored. But what is the reason for the behavior of ultramarine blue? Okay, we know that ultramarine blue is peculiar not just for water sensitivity, but there are several degradation issues that are associated with this pigment. We could also see from the presentation before that is also associated with the formation of oxalates. There are some explanations for this behavior that are proposed in the literature due to sulfur speciation in certain cases, or its action as aluminosilicate catalyst. The thing is that we wanted to try to understand this more, so we use differential scanning calorimetry under nitrogen flow, so in inert atmosphere. So what we do is that we take samples from the paint layers and analyze it, at the beginning daily, and then every few days, and so on, in time. And then the sample is placed in a platinum crucible and is heated up in inert atmosphere, and you see that you have a peak like this that is formed. So this peak is due to the superimposition of two phenomena. The first phenomenon is endothermic, actually, and is due to decomposition, to the thermal decomposition of peroxide species. And the second phenomenon instead is exothermic, and is due to the recombination of radicals that are present in the paint layers and those that derive from the decomposition of peroxide species. The overall effect is exothermic, and the area of the peak is proportional to the concentration of peroxide species and active radical species in the paint layer. These are our paint systems. On the left, again, is linseed oil. On the right is safflower oil. Blue is ultramarine blue, and black is lead white. And so we can see that active species start earlier in linseed oil than in safflower oil, and this is the same for both pigments. But we can also see that it takes longer for ultramarine blue paints to start producing this active species than lead white. This confirms what we already seen also by TGA. But if you look at the temperature that is necessary to decompose those peroxides, you will see that ultramarine blue decomposes at a higher temperature with respect to lead white paints. So the thing is that this means that ultramarine blue stabilizes the peroxide species in the paint layer. Why does it do that? We don't know. The chromophore in ultramarine blue is a radical, so maybe there is an interaction between the radical in the pigment and the radical species that are present in our paint layer. We don't know, but we have been investigating how, for example, the particle size or the treatment of the pigment may affect the reactivity. With Catherine, she's here, and also for completely different reasons with Ophélie and Norbert at the Karlsruhe Institute of Technology. The main thing is that ultramarine blue always pushes towards oxidative degradation. Now, if the peroxide radicals are stabilized, then maybe they affect the reaction pathways. To understand which direction the pathways of reaction go, we probably are biased, but we thought about mass spectrometry. Okay, we will characterize the whole set of molecules that are produced during the curing, and so we will see what are the differences. But to do this with mass spectrometry, we have to do a step back into the simplification of our systems. Because triglycerides or oils, even worse, by mass spectrometry, very quickly evolved to systems that are too complex to be analyzed in detail by mass spectrometry. I'll show you an example. This is 3-linolein, which is the main triglyceride of linseed oil. And let's consider only one path of oxidation, which is the formation of azelaic acid. And so from this molecule, we can have 5 possible compounds, just considering one reaction, because we can have oxidation here, on 2 chains in different positions, on the 3 chains. So if we consider all the possible reaction pathways, this means that very quickly everything will become so many molecules that they will go below the detection limit of the technique. So we said, okay, let's move to methyl esters, because for the same reaction, we have one product of oxidation. We did not invent methyl esters. They've been used already to study the oxidation of lipids. They have been used to study also paint systems, mostly in systems without pigments, using experimental techniques, but also computational techniques. And there is a lot more on methylenolate. This is just really a little bit of it. There is much more on methylenolate. And we decided to use this one because there are published spectra in the literature that we could find that could help us identifying our molecules. We looked at their oxidative behavior in comparison to the oils, and what you can see is that, of course, they behave differently because they are different, but the general tendency towards oxidative degradation is very similar. This is methylenolate, 2 double bonds, behaves very similar to safflower oil, and this is methylenolenate, so 3 double bonds, and behaves quite similar like linseed oil. So we prepare our new sets of paints containing our new safflower model and linseed oil model and the same pigments. And then we started analyzing systematically the products of curing, starting from the volatile molecules up to the cross-link fraction. Here are just a few possible reaction pathways that may lead to the formation, as you can see, of small molecular weight components that can be analyzed by solid phase microextraction, so by simply sampling the vapor phase on top of the paint layer. And then by repeating this sampling at different time intervals, we can look at the evolution over time. So this is the chromatographic profile of methylenolate at 8 days of artificial aging. This is all natural aging. Top is lead white, bottom is ultramarine blue. And this is the evolution of the different molecules with time, up to 3 weeks. Okay, so we see something that was expected. Lead white catalyzes the formation of these volatile molecules because they start faster. And the majority of the molecules that we could identify were expected by auto-oxidation of methylenolate. But we were quite surprised to find these 2 guys here because they are products of oxidation with singlet oxygen and not triplet oxygen, which is the ground state oxygen. We saw something in the literature about ultramarine blue, which is it's hypothesized to be a photosynthesizer in some cases, and so favoring the conversion of oxygen from triplet to singlet, but nothing for lead white. Anyway, we see the same compounds for lead white, for ultramarine blue, but just also for methylenolate kept in the light and in the darkness. So this has got nothing to do with photosensitization, and is probably just produced on site. For example, the recombination of peroxide species may produce singlet oxygen on site in the paint layer. Now, this is interesting because singlet oxygen is very, very reactive, and so will push oxidation even further and oxidize the environment around it. But still, it's not a difference between lead white and ultramarine blue because it was present in both cases. Follow the evolution of monomer species, so methylenolate, monomethyl isolate, which is the main product of oxidation, but also epoxyl groups and hydroxyl groups and so on, by doing GCMS. So the paint layer was sampled, derivatized, and analyzed by GCMS on different time intervals, and then evaluate their evolution with time. Again, we can see that lead white is a catalyzer, no other significant difference, with the exception that monomethyl isolate, which would be the equivalent of azelaic acid in a paint layer, accumulates more in ultramarine blue paints. We could look at monomers and oligomers by solubilizing the paint layers and injecting them with flow injection analysis into a mass spectrometer. We cannot go above trimers, because then the amount of isomers is so many that they just go below the detection limit of the instrument again. But okay, we see monomers, we see dimers, we see trimers, but we also see these clusters here of peak, which are the products of combination between a monomer and a product of oxidation, a dimer and a product of oxidation. So the products of oxidation become involved in the cross-linked fractions. And again, we can monitor the evolution with time. So monomers, dimers, and trimers, and then when we go from left to right, you can see that we have a higher amount of oxygen in the molecular structure. And basically, we can see that oligomers are formed very quickly, but then their content disappears with time because they become involved in other cross-linking reactions, or if their bonds are peroxide bonds, they become degraded with time towards other reaction pathways. But we can also see that ultramarine blue produces oligomers at a slower rate, but the higher the content of oxygen, the higher the amount of these oligomers is with time, also compared with lead white. This could be because they are produced in a higher amount, or just because they are more stable and so they decompose with time and they accumulate. Finally, we had a look at the whole paint layer from the volatile to the cross-link fraction using basically analytic pyrolysis. In this case, we used evolved gas analysis. What you obtain is something like this. You take the sample, you put it inside the pyrolyzer, you heat it up slowly with a slow rate, and then the volatile species that are produced by volatilization at first and then thermal decomposition are transferred into the mass spectrometer. And then for every point, we have a mass spectrum, which is the sum of the mass spectra of all the compounds that are evolved at that time. So this is, for example, methylenoleate paint layer. There is a first thermal zone, which has got mass spectral features of products of oxidation. There is a second thermal zone, which has got the mass spectral features of monomers, and because of the temperature at which this is observed, is also oligomeric species. And then we have a third zone, which is the polymeric cross-linked fraction. Okay, so we can compare the model for linseed oil and the model binder for safflower oil. We cannot compare between pigments because in analytical pyrolysis, the pigment plays a fundamental role in determining the pathways of reaction. So we cannot look from here to there. We can just look here and here. What we can see is that in methylenoleate, so in the model for linseed oil, the cross-linked fraction is more thermally stable, which means that it's more cross-linked and also less polar with respect to the model for safflower oil. And we can also see, and this is only true though for lead white, is that the polymeric fraction is significantly more abundant when the model for linseed oil is used instead of the safflower oil system. We can also monitor what happens with time. This is methylenoleate with ultramarine blue and with lead white. And because this is mass spectrometry, we can look at the evolution of single ions. And so what you will see in gray and in red are products of oxidative degradation. And these are, and in green, the evolution of the polymeric network. And so what you see is that in ultramarine blue, the cross-link fraction, which is here, becomes more oxidized with time. In lead white, instead, the cross-link fraction is not highly oxidized. The degree of oxidation decreases with time, and we had a steady increase of the cross-linked, highly cross-linked fraction of the polymeric network, which is quite stable across time in methylenoleate. So, to conclude, the pathways of reactions are the same from the qualitative point of view. We cannot observe different sets of molecules in one system or another. but the kinetics are different, and is also different. The profiles are also different from a quantitative point of view, because the ultramarine blue picks more oxygen during curing. This oxygen becomes involved in the structure of the polymeric network, so the cross-link fraction are oxidized themselves, and also the degree of cross-linking is less extended compared to lead white, which is very good at promoting the formation of carbon-carbon and carbon-oxygen-carbon stable cross-links in the paint film. So we believe that methyl esters are quite nice when you use them with mass spectrometry, but of course, as you can see, very quickly after a few weeks, the system is so complex that the information is not there anymore. This is even more true if we use triglycerides or oils. And so I think that the combination with computational modeling would be really good to pick the experimental data and then projecting them in the longer term to try to predict what is the structure of these molecules, these cross-link structures that are formed with time. The structure, the molecular structure of this cross-link network is not clear yet. We are not there yet, and there is still a lot to do. Mass spectrometry becomes almost blind very quickly. There are experiments that we would like to try using high-resolution mass spectrometry, but that will stop at the oligomer structure, and then we will need more to go into the whole cross-link network. We have a collaboration now with Loïc and Laurent here in Paris, and with Uwe Bergman at University of Wisconsin-Madison to try to look at these systems with a different angle. I'm concluding saying that I think that the degree of cross-linking of oxidation or oxidative degradation undergoing by a paint layer with time are really important in determining the stability and the behavior of a paint film. We still miss an important link here, which is the chemical, molecular information and the mechanical properties of the paint layer, and also the rheology of the paint, because, for example, the pretreatment, as was shown before, has not just an effect in the time that the paint takes to dry, but also in the rheology, which is what interested the painters when they were preparing their paints. And I think that also the study of the curing is very useful to try to help us understand what happens with time in this system. I finished. I need to thank all the people that I've been working with, the group of the CMOP project, and then lots of people from Pisa University. Thank you.